This video will continue our discussion of Green's theorem by relating it to flux. The other form related to circulation, remember circulation is related to work, so that Green's theorem helped with circulation with work. This is the Green's theorem, and I'm not going to prove it, derive it, but this is the theorem that will help us with the flux definitions. Now remember that circulation was the measure of how much headwind or tailwind that we have, how much it helps us. The flux measurement is a measurement that helps us understand our crosswind, right? If it's a positive, then we have crosswind a lot of crosswind going from left to right. If it is a negative, we have crosswind from right to left. If it's zero, we don't have crosswind at that point, or whatever we're measuring in a space on a curve. All right, so this form, we have these same requirements that we had for circulation, simple, close, counterclockwise, and then the space has to be connected and simply connected. So we need to check those. The vector fields derive the same way. Now this looks like something we've done. Remember, this is our flux measurement, which also can be written this way. But now we're writing it with this circle there. Remember, that means that it's simple and closed. And the definition, if we look, the differences between Green's theorem related to circulation is that this is a plus. And then notice that each one of these, like m usually is with the other variable, like related to n, meaning like y, but it's actually m with the associated variable I, x in there, and then n with the associated variable y. So be very careful in my calculations, even in videos I've recorded before, I make the mistake and put a minus there, and then I confuse myself in the video and I correct it. So just be very careful. So let's do an example of this. Use Green's theorem to compute the outward flux of a radial field. So a radial field, remember, is it's going to shoot vectors out in every single direction, and it's going to get bigger as we go out away from the origin. Across the unit circle, and they want us to interpret the result. So let's try to use Green's theorem. We still have to check our path is the unit circle there with radius 1. It is definitely simple, right? It doesn't cross over. And it is closed. It means it starts and ends at the same spot. The region R is connected, meaning if I put 2 points here, I can connect them and stay in R. And then simply connected, meaning I can draw space, an open space, and contract it down to a single point. This means we can use Green's theorem. All right, so we need to calculate. We have our vector field is equal to x, y. This is mn. And we need to derive the partial of m with respect to x, different than circulation. M with respect to x is a 1. N with respect to y is a 1. And be careful here, we are not going to subtract them, but we are going to add them. Right? This doesn't tell us anything about conservativeness. We don't have any theorems leading to that. There may be some that exist, but none that we have talked about. So now we can actually take the integral. It's going to be the integral over path C of x dy minus y dx. And this is the same thing as the double integral of r of 2 dA. And we actually can get the this is what, if we just understand what an integral means, this means 2 times the area of R. Well, R is a circle, so it's going to be 2 times the area of R. That's all that integral means. So we have to be careful there are variables there, right? We'd have to run that differently, but it's a constant, and we could pull the constant out, and then it's just the area of R. So this is 2, and then pi r squared, r is 1, we get a pi. So that means that the area, right, it's based off the area there, but the work, or the flux, sorry, we're not doing circulation, we are doing flux, is a 2 pi. This makes sense. If we're going around that way, we remember our vector is of the vector field is radial, going out like that, so it sweeps across, meaning the flux should be a high positive number because there is a whole vector or force coming across the front of us from left to right.